Welcome to Industrial PLC Applications Level 1. This is week 5 in review, working with timers, an introduction, and exercise number 5. The first part of our lab looks at the program select to see another application of interlocking. So part 2 of the exercise was to open and examine program _select. So I've done that, and we can see we have a single rung of logic that has two inputs repeated, DI08 and DI09. And depending on the condition that these two switches, these two inputs are, will determine which of the outputs, TP_prog, TON_prog, and TOF_prog. So digital input 8 and digital input 9 are on the trainer, and they represent the two contacts, the two active contacts on the 3-position switch. So right now the switch is in the neutral position, so it's not making DI08 and it's not making DI09, and since it's not doing any of that, we're going to turn on TP_prog. Now to find out what that does, we can right click on it, go to cross-reference, and on the bottom we're looking for the write instruction. So there's our variable name, user, global, got it, good, TP, timer, and program select. So the write is in our first program, which is where it has it here in the bottom, and our read is in a program called TP_timer. So if I double click on that quickly, it jumps right to the program and to the location of that particular contact. So if I change the state of my rotating switch one position, I have now energized DI08 but left DI09 off. So that now brings us to this TON_prog, and if it's true to form, I'm suspecting it's going to control this other program, TON_program. If I rotate the switch to the center and then off to the right, I'm now looking at DI08 being off and DI09 being on, and I will execute TOF_prog. Now these three outputs, they don't follow the same graphical description of _IO, _EM, _DO, _something, because these are internal variables. They do not exist in the real world. That is one of the largest advantages that PLCs have over relay logic. You can have an infinite number of internal coils and contacts that you can use to resolve the logic without having to do any wiring. There's no troubleshooting, there's nothing that can get burnt, there's no contacts that can fuse or get corroded. You just solve it internally and then execute on the outputs. So this method of using the two switches, in theory, if you're sitting there thinking, well, you could have used one switch, and that's true. You could have done that, but the problem is you still would have required both of these off as a minimum to get TP_prog to work. The other problem is that without interlocking, the difference between a switch that has failed and a switch that is left in the open position, well, the wire's off, it's like open. So you may not get the signal that you want. Conversely, if a contact weld shut, then it's always on. And when changing the state, you're giving yourself, with the interlocks, you're giving yourself two conditions to rely on to change the outcome of the rung of logic. One thing that I want to point out before we leave this program select, and that is when you look at these two bits, if you think of it in binary, you have up to 4 different possible conditions. There's 2 bits. 2 times 2 is 4. That's the number of combinations you can possibly make. Now, on the truth table that's to the left, you can see that we have the different combinations, but the one that cannot be made and that's not in the program is another branch that has both of the inputs true. And the simple reason for that, of course, is that the switch does not mechanically allow you to do that. But in other instances where you have a different switch configuration, having another state because the 2 are both on gives you a 4th possible outcome. This is exercise 5 part 3. We're going to look at on-delay timers, known in Connected Components Workbench and others as a TON or ton. Now it's time to take a look at our on-delay timer. Now, to begin with, you may notice there seems to be a problem with our project. We already have an output turned on because our TON prog bit is turned on. So while executing the exercise, there was a step where you were to change this so that we can seal this in but shut it off, and we don't want to have the same bit that's controlling the whole program controlling this. So we're going to go offline and we're going to do a quick edit on that, and I'm going to use our stop push button. So that will interrupt that. As long as it's in the closed position, that'll still run, but if I press it, it'll open up and break that seal. Now if I place that there and that's closed, that's going to do the same thing we did before, having that. So what we have to do is we have to kind of move this outside of that sealing branch so that when we open it up, we'll just defeat this because it's going to defeat that, and there will be no path to make that true. So when you go to make edits like that, make sure you take a few extra seconds to think about what it is you're trying to accomplish. By just changing that there, it's essentially doing the same thing as we had it because this should already be energized. So we're going to turn around and we're going to reconnect and download. One of the things that we like to try to do while you're learning to program is to identify patterns and to identify mistakes. It makes it easier for troubleshooting in the future, but also it helps you to critique your own work. And there's lots of times it doesn't matter that you make mistakes. It's perfectly safe, and I personally, when I program, I'll do one rung at a time. Try it out, make sure it's behaving the way I want. Add the next rung, try the 2 of them together, etc. I build upon success, and if it doesn't work, well, as Thomas Alva Edison said when asked about how he had the patience to go through 1,000 failures, he said when he was making the light bulb, he said there weren't 1,000 failures. I just figured out 1,000 ways how not to make a light bulb. Anyway, okay, so here we have our timer. Now, a ton timer or on delay timer, the Q is not going to execute until PT and ET are equal. But it has another condition, and that is this input must remain true. So I'm going to push my input 10, and I'm going to hold it just for demonstration purposes. And you'll see it's a 5-second timer. And when it reaches 5 seconds, the output becomes true, and now I've sealed it in. And if I release the timer, what's going to happen is, watch the ET as I release digital input 10. So it resets itself. The ET becomes 0, and this is no longer true. So anytime that the input is made and lost, it's going to reset the ET, and it's going to turn off the Q. Now, the person who programmed this obviously was trying to be clever, because when the push button is pulsed and let go, there's a seal in here to keep it running for the 5 seconds. And that has to do with this output, this DO02, and this instruction here called reg. Reg stands for rising edge, and it's a function of the timer itself. When you start a timer, and let me just go into the variable monitor. When you go into a timer like a ton, this component, this bool, this TON_reg, it looks to see that the rung ahead of the input was false and turned true, and that's a rising edge. Now you would think, well, as soon as you turn it on, why are you looking specifically at that leading edge? What possible difference does this make? When timers only had a tenth of a second and a second, or a millisecond and a second as its time base, you had those two choices. If you had it set to a second and your scan time is running at half a second, it didn't make any difference. It was not that sophisticated. It didn't matter. However, as the processors got faster, as the logic got interpreted faster, they were discovering very quickly that what would happen is the timers were not starting on time. And by examining, if you imagine this box as being our false to true, let me just move that up so it's on a line here. Okay, so the red line is our 0 and this blue line is our on. So if we're 0 and we pump it up to the top to say that we're on, in the older, slower ones, anytime along this blue band that I'm pretending to be the top of my pulse, anytime I was doing that would be valid to start the timer. But let us say that in the middle of its scan, it doesn't detect that rising edge until where the cursor is now, somewhere in the middle. This whole portion would not be counted towards the total time. So by looking for that trigger, that rising edge, it's saying the second you see that, that's when your timing starts. And if it happens to miss it during a scan, it knows the last scan and it can actually timestamp it and look back and go, okay, I've got to add that to the time. So sometimes you'll see the timer, it'll just suddenly jump a number, and that's what it's doing. It's saying, whoa, wait, hang on a second. Reg started 27 milliseconds ago, so I've got to add that back because I can look at my previous scans. The sophistication of the processors now are a lot greater than they were when I first started programming. So by using this rising edge, they know every time that a timer is initiated, its time is going to be based on that leading rising edge, otherwise known as the false to true transition. Now we saw that false to true transition back in our timer pulse. Close that for a second. Go back to our timer pulse. And when we looked at it, it also had a rising edge. And it functions there a little differently, because when that rising edge was triggered, it was latching up an internal bit within the construct, none that we don't see or can't address because it's strictly into the operation. It's like taking a wristwatch apart that has springs in it and saying, well, let's take a look at the spring. Once the spring's gone, it doesn't work anymore. Same idea here. We don't need to look at that. We only need to understand that it's there. And what happens with this instruction is, once it sees that false to true transition, that rising edge, that's the starting point of its cue, and it's going to leave that on. And as you noticed, when we were using that program, turn it back on for a second, press that button, it sees the rising edge and starts. But when I let go, the rising edge is held. And it's going to stay held even after the timer. It's going to clear up when the timer's done. But pressing the start again, it's ignored. Doesn't matter how many times I press it. because once that timer has started, it's going to complete its job, and it's going to look to see reg go from true to false, and it's going to wait for that next rising edge before it will allow it to start again. And in the time that I did that quick double shuffle, that it was recorded internally and said, oh yeah, we were just finishing, our scan was finishing, and there was a press to start again. So it may look like an optical illusion, but it's not. It's actually doing its job. Once the timer is finished, reg is reset, and it will not start again. That reg will not be cleared until it sees that the timer is complete. Once the queue is done, the queue has a falling edge, and that resets the reg. Similar idea that's going on with our on delay timer. It's looking for that rising edge. That's when the timing starts to count. Now, with the TON, anytime during the cycle, if it loses its input, what happens is the timer drops out. And in this case, rung 2, we're going to start that. We're going to seal it in because we're going to use reg to our advantage, because I don't want to hang around for the whole 5 seconds to hold the button. Change our program again. Okay, then I'm going to press my button and let it go. And the second the timer starts, reg is given that false to true transition, and it becomes active. Now, what we're doing here in rung 2 is a bit of not logic, because we are using the time that the timer is actually counting, it's timing out, to do some work. We're putting the not logic to work. Notice the first contact is TON_1.Q. So that's this queue up here. So this queue is not running right now because the timer is not running. That makes sense. But if we didn't have this other contact, the digital output 2 would be on as long as that timer is never on, which is not really what we're after. While the timer's timing, but it's not finished, we want something to happen. So it's sort of like if you wanted to turn some lights on and it's still dusk out. While you're waiting for the timer to trip, you've pushed it on because you know that it's going to be dark in 10 minutes, so you start the timer to turn the lights on in 10 minutes. You can still do stuff while it's dusk, and then in 10 minutes the lights comes on, and now the lights are doing their job and everything's good. So it's the same idea. While this timer is actually counting, once reg has been made, it's been tripped. The input's still true. Reg is true as long as the input is true. Then it starts to count, and once the queue is finished, well, then our Q naught is not true anymore. So it opens up the rung. So let's watch that again. So we're going to push our DI 10. We're going to let it go. Reg is made and my Q is not finished. The second the Q is done, it's no longer true. Reg drops out. We lose our seal. We're no longer timing, and therefore the queue gets reset instantaneously. Really, really fast to watch. Let's take a look at it from the inside. Go to our variable monitor. You still probably won't see the transition, but you can still watch. The in will become true. The program time is still there, and we still have our ET. So I'm just going to pulse that once. And reg has been set and is still set. Q will flash on, and it happens so fast because it instantaneously resets and pops out. Now below that, we've captured that by turning on digital output 3, just to show that it's been done. So I'm gonna reset digital input 7 by turning it off. Okay, so that digital output's through. So let's prove that TON1.Q is actually doing its job. So I'm going to press the start button, and this only seals in because this had to have been true. it flashed on for a second and it dropped out. Every time the in drops, the TON timer will stop. So if you need something to start and run for an hour, you're going to delay it starting for whatever reason, maybe a warm-up period, cool down period, etc., then you'll still use the TON, but the input must be maintained true. I'm going to hold the input on now so that even though TON 1 will be not true, we've now dropped out DO2, but I'm still maintaining my input 10, so it's still true, and my output is still true. And if I press the stop button, it'll break the seal on that bottom run. Second I let go, because the TON timer is still armed, it still reloads and turns on digital output 3. Now, an interesting thing happens. We have this TON timer and it's going to reset itself if you let go of the input. There is a way that we can utilize another timer to make it do some more work. And it's called cascading.
Alright, so I've made some changes to our program, and you can see it's actually quite a radical bunch of changes. But what I've done is I've used a one timer to trigger another timer, and they call this cascading timers. And you'll see that if you have a timer, say one conveyor that's running and it takes time to get up to speed, and you don't want to start the next conveyor until the first one's up to speed. So you would say, okay, it takes 15 seconds for this one to get up to speed. So at about 9 seconds, we're going to start the other one, and it's going to take 15 seconds. And then at 9 seconds, as it's speeding up, we'll start the next one. So anything that's moving along 3 different conveyors can be moved along in a nice orderly fashion. So what I have is on my first timer, I'm using the second timer as being not finished as part of my control. So they're free running at the moment because there's not a push button that's starting the whole process. So the first timer is going to count for 7 seconds when it's true. When it's finished, its TON_1.Q will be done, and allows this timer to start timing. So we can see our digital output 3 will be on, but only for 5 seconds, not 7, because it's the 5-second timer that's finishing its queue, which then triggers TON 1 to start again, and the queue isn't set by the TON 1 until it's completed its 7 seconds. So you get this asymmetrical flash on it, and if you can see on the little miniature camera view that I've got, digital output 3 comes on for about 5 seconds, shuts down and stays off for 7 seconds. Now there's a separate timer that will do this, and it's called a TON off, which is a time on, time off timer. And we're going to look at that. And you notice that very, very briefly that digital output 2 flashes on because TON 2Q is done. When it's done, it flashes it on momentarily, and you might not even see it, and occasionally you'll see it flicker just because it happened to register at the right time to trigger it through the scan to say, oh, well, by the way, I'm on. Yeah, okay. There it was. Very, very short. Okay, so let's do a quick recap with on delay timers. 1, the input must remain true for the timer to actually execute. Anytime the in is removed, whatever the elapsed time is zeroed out. The Q only becomes true when the ET equals PT, and will only stay true if the input stays true. You can use the reg with the not Q to have something work while the timer is counting up and finish when the timer actually is complete, so that you're using that not Q and then with the reg with it to make that happen. It is triggered by a rising edge, which is hence the name reg. And this is part 4 of exercise 5. we're looking at off-delay timers. In Connected Components Workbench, they are called a TOF or TOF. Alright, we're going to look at the off-delay timer, the TOF, and a lot of electricians find it very frustrating because they're used to using the on-delay, and in this case we're actually looking at the reverse. Think of a TOF as a shutdown procedure. For example, you can have very large fans that will take a long time to shut off. So you can use an off delay so that if you have 4 of them in a sequence to cause a wind tunnel, you don't want to turn off them all at the same time because there'll be motor generating going on. So you'll start with the first one and you'll just hit the stop button. It will shut the motor down, slow it down, slow it down, slow it down, and then shut it off. And then the next one will do the slow it down, and shut it off, etc. So we have on our program here a TOF that is programmed for 5 seconds. And right now its Q is turned off. And if we look at the next run, the TOF_1.Q is false, therefore my output 8 is false. And if we look at our trainer, we find that digital output 0 is on, which is the not TOF, and it looks for a falling edge, so the not TOF fedge is also off. Therefore, we have our output number 9. Now, when I press my input, in this case it's DI11, I'm going to push DI11 and I'm going to hold it. It's a maintain a momentary contact push button. And we see in our program that it livens up. The 5 seconds, however, has not been triggered. That's because our falling edge has not been detected. It's looking for that true to false transition, not false to true. So right now it's showing us that the output DO8 is on. And when you energize a TOF, it turns its Q on immediately because that's what you're looking to control. So if this was not a momentary, but say a toggle switch where you toggle it on, the fan's running, and now you want to do the sequential stop. So I'm going to release the push button, and we're going to take a look at what happens to DI11. DI11 goes false, and now my timer starts to count. The output 8 turns off once the timer is complete. So I'm going to reset my start by pushing the button, and we see that digital output 8 is now on. Digital output 9 beside it is off. I release push button, it stays on for 5 seconds, and then the other light turns on. It's a little tricky to work with, but once you understand the mechanisms behind it, it's actually quite simple. What I'm going to do at the same time now, I'm going to open up the variable monitor. I'm going to just go here, and we can watch the different contacts in action. Okay, so here is our TOF. And let's set it off to the side so we can watch the outputs. We don't need to see the inputs because we have the outputs to monitor, we have the time and the TOF and the input. So right now my TOF.N is not energized. I'm going to push the button, and now it's energized. We can't change its logical value, so it just says it in the background. My Q is turned on, and so is my dot fedge. So the dot fedge is looking for that true to false transition, and nothing's going to happen until it sees that. So on my timer, it's primed, my Q is turned on, my output DO8 is turned on, and my digital output 9. So it's 8's on, 9's off. Okay, so I'm going to release the button, and on our monitor we can see that fedge has detected a drop. Therefore, the timer is set to go, and then after 5 seconds, the Q drops out. That's pretty much the whole shebang with a TOF. Again, much like the on delay timer, you do have the capability of using the not condition of the cue, and in this case we're using the fetch. If you watch the operation, realistically, because it's looking for that fetch, it's not really necessary to make that run go. You can see it's ahead of the dot cue, which you can just wait for the dot cue to energize that. Now for part 5 and exercise 5, we're looking at a timer that's a timed on and a timed off timer, otherwise known as a turn-off. Alright, so now it's time to look at our timed on, timed off timer, otherwise known as a turn-off. Its primary function tends to be for a flasher, something that's short and quick and in between. But it's not limited to that. There are a lot of things that you could control if you had a period of on and off that was cyclical. For example, if you were using a mix machine, and if you had it constantly agitating all the time, it might introduce too much air, so you let the agitation stop and rest, especially when it comes to large tanks. Too much agitation can create air bubbles. So you can use a long-term turn-off to cycle it on and then cycle it off. You wouldn't need to put a 24-hour clock. You would just simply say, okay, so in this large vat, I want to keep it stirred up just so that it doesn't solidify. So every 2 hours, turn on for 2 hours, or every 2 hours, turn on for 15 minutes. And you can do that. Now, when you look at the instruction, the first thing that pops out is it's got an extra box on our input side. And I have 2 different time bases on there. I have T hashtag 400 milliseconds and T hashtag 200 milliseconds. So these are the periods of time that the timer will be on and the period of time that the timer will be off. And the elapsed time, at some point it was running because now it is stopped at 200 milliseconds. The cue is not turned on because the logic ahead of our timer is not true. So if you look at rung number 4, our turnoff_1.cue is turned off, therefore it's false, therefore rung 4 is active, and we have our digital output 1 light turned on. Now it's going to flip-flop with digital output 0 when the timer is activated. When we did timers many years ago when PLCs were a lot slower, you could create something called a free-running timer. And I'm going to take a second and show you what we mean by that. So I'm going to disconnect. And we did that sort of when we did our timer program. So I'm going to add a run here. And what we would do is we would take a execute if off, and we would put a TON timer, and the TON timer would be controlled by its own output. And then we could put the time base 1 second, and what would happen is it would be called a free running timer. It would constantly reset itself, and you could then use the cue as an output to turn on a flasher. Now, I've said in the past that it's not a great practice to put the output on the same rung as the timer itself. And the reason I say that is because you'll run into problems when you start thinking, oh, I can just put stuff on the end of that and it'll work. Especially when you're using the not cue, you end up with problems. So old school was not to put the timer, but I'm going to break my own rule just for demonstration purposes, because I just want to turn on an output. I'm going to use D06 to show you it will even see this one flash. So I'm going to turn this on, download it and turn it on and execute it. So in theory, this light here should be flashing once a second if my free running timer works. Okay, so there it is, and you can see the time changing very, very quickly, and my output, if it comes on, is just for a tiny split second of a time, literally, even though it is a 1 second timer. And that's simply because the refresh rate is so much faster than they used to be that the scan just blows right by it, and it barely has enough time to energize that, which for a flasher doesn't really help us. Now, when we did our on delay timer, we could use 2 of them and make them flip-flop amongst each other to create a flasher, which was a lot of programming. Well, we don't have to do that anymore because we have this one simple instruction called a turn off. So with the turn off, you've got the 2 different input times, but you need to put the not done cue ahead of it. That's the heartbeat, because it needs to see that, just like other timers, it's got to see that falling edge or rising edge. Let's take a look at the components inside of our turn off. And we don't want that. Let's open that up. And look, it has a reg and a fetch. So at one point of the program, it's looking to see its rising edge, that false to true transition, to do half of the program, and then it looks to see that drop down, that falling edge from true to false. Without those, the program doesn't work. Right now, it is seeing a falling edge, so in order to trigger it, it needs to see a rising edge. So let's see if I can shove this off to the side. Make it a little smaller, hopefully. Please cooperate. Thank you very much. Okay, so can we sneak it up the bottom too? Excellent. Okay, so now we should be able to watch the outputs. So I've got an input 12. It's going to start a flasher and it's going to seal in. That's going to start my process. That I could make this free running right off of the rail, but in an operational sense, we want to have something to control it, and we want to have a way to turn it off. In this case, I have a normally closed push button number 5. It's a red one on my trainer, and what's going to do, it's going to open up that circuit. So I'm going to press 12. It energizes my flasher, and it starts my turn off. And you can see that the reg and fetch are being activated at different times, and the 2 outputs are flip-flopping depending on whether I'm on the running mode or the off running mode. And up at the top you can see them flash, and it's not symmetrical because my 2 times are off. So what I'm going to do is I'm going to stop this for a second by pressing this, and I've got the 2 times here, and you can't change them on the fly. As much as I want to change them on the fly, I can't. So what I've got to do, okay, no, I can't change it there. Okay, I got to go offline. Turn that, go offline. I'm going to reverse these. So you saw how it was flashing, but one was going flash. So I'm going to change these. I'm going to spin this around. I'm going to make that 200. I'm going to make this 600. Okay, big change. Came down from head office, mission critical. Let's change it and watch what happens to the light, to the lights. And this goes on quite often. There's another thing I'm going to show you that's done quite often as far as programming goes. Okay, okay, we're going to press our start button again. That was number 12. And you see now the status of the 2 lights have changed. Now, I don't have to use 2. I'm just using that because it's visually easier and quicker to see. I could have had this just 1 flash, in which case you would have noticed it would have stayed on and flashed off. You could have a series of different times in here. This particular arrangement might be to say that it's at a particular part of its process. As it's filling up, maybe you want something to flash a little faster. So if you wanted to use that one turn off to change the rate at which the light flashes, so it's very slow when it's just filling up, and the faster it goes, the more the tank fills up, the faster it goes until it gets to the top and it's really going fast, like it's going to overflow. You can do that. But that would mean going into our program and constantly changing this every time we want to do that. So there's an instruction that they use, I'm going to disconnect, and it's called a move instruction. And what you can do is, instead of using these hard fixed constants, the T data, time data type constant, you can create a move instruction. So if I were to take, say, my push button number 1, so I'll just, what I'm going to do here, I'll just create a branch. And put in a contact. I'm going to use my number 1. And then I'm going to put in a move instruction. And what a move instruction does, it says, look at this location, what's ever there, put it here. So for my output, this is where I'm going to use my turn off. I can redirect this, but I can't just put it in the turn off. I have to put it into a variable. So I'm going to create a variable, and I'll just call it new time because I'm so creative. And I'm going to right click on it, go to my variable selector, and it's a bool. We don't want a bool. What we want is a time. Scroll down or just type TIME. And I can give it an initial value here, and I'm going to call this the T hashtag 500 milliseconds. Now, what's critically important here is that this variable that we're creating must be the time data type and must be a valid time. You still have to use the hashtags. As I like to say, you can't put a Mack truck into an orange. If they're not the same, it's not going to fit, it's not going to work, and it will fault out the processor. This is where, using a variable, if you're doing math on a variable, you can create a negative number. And the second you create a negative time, you will get a major fault on your processor. Okay, so that part's done. And here, I'm going to type in new time. And we know that the original new time is 500 milliseconds. So here, I'm going to go T hashtag 600. Well, let's make it a 1 second. Double up the time. So when I press the start button, it's going to take this 1 second. It's a time data type. It's going to put it into new time, and new time is then going to be sent off to our timer. Now, if I've done my job correctly, I should be successful. I'm going to shrink this back, zoom back just a bit so we can take a look. Cross my fingers. Hope I didn't make a fool of myself. Now you notice that when I'm making changes to my program, all my outputs go off. Anytime you go into program mode, you disconnect the output from the PLC. So because you're making changes, the safest thing to do is turn off the PLC. Like disconnect it as far as the instruction goes. Okay, so right now, my new time is set at 500 milliseconds. And I'm going to start my button by pressing the 12. And we're off to the races. And we can see that the time is 200 milliseconds, 600 milliseconds off. So it's pretty close to being the same. So now what I'm going to do is I'm going to press my start push button. And let's look at what happens to our new time. And now all of a sudden it's 1 second. And you can see that our pulse has now completely changed simply because I've changed the time on it. We're looking at digital output 0. So you could have a whole series of different instructions, and every time you activated one of those move instructions using a time variable, you could then rewrite and have that flasher change at different pulses. So if you had a table that when the tank is almost empty, have a long steady flash, it's empty, and then once it's down to the point below the level you want, you can have a non-stay on the time, like we got a red light. Then you could turn around and say, okay, as the tank's starting to fill, then you would start to get it to flash quicker and quicker and quicker until it got to the top and go, hang on, stop, it's almost full, and or whatever would be the case. And they do this quite often. They will use timers, or they will change speeds on the fly by using an internal variable. So that's the TONOFF, the timed on, timed off timer. The next one we're going to be looking at is the last in our list, which is an RTO timer. This is part 6 of our exercise 5 on timers, and it is a retentive time timer. All right, our last timer to look at is our retentive on timer. So a retentive on timer, its job is to keep track of a total amount of time. And you'll notice that we now have an extra box stuck in the middle on the input side of our box instruction. So we have our input, we have our program time, total time we're going to keep track, and we have our elapsed time. Now, the total time, you can think of this in a bigger sense. You could time that to be 30 days, capture all the time up to over 30 days. You could do it over 24 hours. RTOs are normally used to keep track of progressive amounts of time. So right now I have my program time set at 300 seconds. I have my elapsed time, but I have this RST. Right now it's looking at digital input 3, which is another push button. It's looking for this push button to be true, and when I press it, it'll go true. And what this does is this resets this clock so that the elapsed time disappears. So I'm going to start my timer. I've got 2 different inputs. Where these are used quite often is, say, for maintenance. Robots don't have odometers because they don't do any mileage. Tractors are the same. They might have a speedometer, but they won't have an odometer because tractors can be running idling, doing nothing for a quite long time, especially if you're using a PTO to run something other than just driving the tractor around the field. So in order to maintain it, they have an hour meter. And after so many hours, you've got to change the oil, you've got to change the grease, etc. You've got to do maintenance on your tractor or risk running it and destroying it. And the price of tractors, you don't want to do that. So I have 2 buttons that can activate this timer. I have 10 and 11, so I'm going to put 10 on. And you can see our timer is actually beginning to accumulate some time. And when I let go, it stops. And I turn the other one on. Turn them both true. Every time I drop one out, it gathers some time and then it stops. And it keeps maintaining this. It will not turn on the cue until the PT equals ET and I have 300 seconds, which is going to take some time. So over the course of a day, say you're running a small factory or something, and you're trying to keep time, how much time am I losing because the machinery is going into manual for some maintenance. So anytime that someone would put it in manual, you'd be logging that time. And anytime that someone was stopping it for whatever reason, you could have another push button that would count that. And both of those would be triggering the total elapsed time. So at the end of the day, someone from accounting can go up and say, okay, can you print off a report, and I want to look at all these RTOs. And it would say, okay, you lost, in this case, between maintenance and manual mode, you lost a total of 19.98 seconds. Well, that's hardly mission critical. But if I'm running over a 24-hour period, you know, if you get up into the 20 minutes a day, especially if you're in a large assembly plant, 20 minutes a day is, that machine's not doing its job. Depending on what you're making, times that by the number of minutes. Like where you make a car, the entry level price of a car now is 35,000 Canadian, and they put one out every minute. So $35,000 times 15 minutes, that's a lot of money. So they want to keep track of that sort of thing. There's other purposes and uses for it, just again for cycle time, etc. You can have a fault counter, how much time lasts during a fault, etc. So when you program it, remember you've got the 3. You do not have to have a reset. It'll still work. It'll still accumulate the time. It'll set the output when it's finished, but you'll have to manually go and change it. So that concludes the exercise. We've covered all the timers. We've covered everything from a pulse time to a on delay to an off delay, timed on, timed off, and finally an RTO timer.